Let's elucidate the quantum order finding subroutine of Shor's factoring algorithm. In this video, we will see how to adapt quantum phase estimation to solve the problem of order finding. We will explore this quantum circuit diagram, and we will mathematically describe the quantum state at 4 key stages in the order finding algorithm. Before we explore this diagram, let's review what we learned about the quantum phase estimation algorithm. Previously, we explored the exact case of the quantum phase estimation algorithm. In general, the target of phase estimation is the L-qubit unitary operator denoted by capital U. This unitary operator has an eigenstate labeled by lambda. This eigenstate is associated with an eigenvalue of the form e to the 2 pi I phi, where phi is the phase that we are trying to estimate with this algorithm. Because we're dealing with the exact case, we will be able to exactly determine the value of phi. And if we know what phi is, then we know the eigenvalue associated with this eigenstate. In the quantum circuit diagram, let's have a look at the register on the right, that is register Y. This diagram depicts each of the qubits in register Y being initialized in a single qubit computational basis state. So lambda sub L minus 1, lambda sub L minus 2, all the way over to lambda sub 1 and lambda sub 0, these are bits. And these bits can either be 0 or 1. And the bits serve as labels of qubit states. So they label which one of the computational basis states we're dealing with. If we take the tensor product of all L of these qubits in register Y, then we're going to get the eigenstate. So have a look at the notation up here in the top. The L qubit eigenstate is expressed in this format. Implicitly, you can imagine tensor product signs occurring in between each of these single qubit states. And in total, we have L of these single qubit states. They're all getting tensor producted together to give us the L qubit eigenstate labeled by lambda. So that is why we have an L in the superscript. This superscript L distinguishes this state from a single qubit state. It is not the state of a single qubit, it is the collective state of an entire register of L qubits. Note that this definition of the eigenstate is very restrictive. We're only allowed to initialize eigenstates that can be expressed in this format. So if you can't express this eigenstate as a tensor product of all of these single qubit states, then this diagram is not going to make much sense. So we can actually imagine a more general type of eigenstate. We can imagine a general state that does not have to be initialized in this format. So we can get rid of all of these labels over here, and we can replace it with just the state lambda. So imagine that there is just a collective state lambda over here. So even in that really general scenario, where we have some really general initialization procedure that initializes the L qubit eigenstate lambda, we still need to know what that eigenstate is. So to perform this procedure, we need to have information about how to apply the unitary operator U, which is the target of phase estimation, and we also need to know what this eigenstate is, because it is essential to initialize register Y in that eigenstate. And that allows us to perform this procedure. And we looked at 4 key snapshots in this procedure. We had initialization, that is the green snapshot. Then we had creating superposition, that is the blue snapshot. The red snapshot shows us what happens after we perform this sequence of controlled unitary gates. And the purple snapshot shows us what happens after we perform the mu qubit inverse quantum Fourier transform to register X on the left. And after this purple snapshot, we can perform measurements of all of the qubits. And we're not really interested in the results of the measurements of register Y. We're only interested in the results of the measurements of register X, because it is the measurement of these qubits that's going to give us this sequence of bits over here at the very bottom left of the diagram. And this sequence of bits is actually used to define phi. And because we're dealing with the exact case, phi can be exactly expressed in terms of these mu bits. You can see these mu bits are occurring in a sum over here, and they can be used to express this as a binary fraction. And a convention that is used throughout these videos is that this subscript over here tells us what power of 2 we need to multiply by. So you can see that in this sum, when we have phi with a subscript minus j, this term is being multiplied by 2 to the power of minus j. And if we look over here in this binary fraction, this first bit that appears in the sequence after 0 point, then we have phi sub minus 1. This phi sub minus 1 is being multiplied by 2 to the minus 1, which is 1/2. So this is the 1/2 term. And then we have the 1/4 term. And we can keep going all the way to the final term, which is 2 to the minus mu. So that's what it gets multiplied by. But all of these phi's with subscripts, they are bits. And together they can be used to define this mu bit phase. But in general, if we're not dealing with the exact case, this is just going to be an approximation of the phase phi. And when we adapt this phase estimation algorithm to solve the problem of order finding, we're going to see that we're going to need approximations. So we're just going to be doing approximations. One essential thing that we've kind of overlooked in this procedure is that we're assuming we have knowledge of how to initialize the eigenstate lambda. If we don't know how to initialize the eigenstate lambda, then we won't be able to perform this procedure. But there is a trick that we will implement when we describe the order finding algorithm. And that trick is to actually prepare a superposition of eigenstates. So we're not going to initialize register y in a single eigenstate, like we're doing in this diagram. Instead, we're going to initialize it as 1. So by 1, I mean a string of L-1 zeros followed by a 1. So that is the binary representation of 1 as an L bit string. So if we do that, then we're going to actually initialize register y as a superposition of eigenstates. So in this diagram, we don't specify what this unitary operator u is. So we're leaving that open to interpretation. And this works in general for a given unitary operator that acts on L qubits, as long as we know what that eigenstate is. But just know that we're going to have to adapt this to solve specific problems. So now let's move over to the order finding algorithm, and we're going to see some of the similarities and differences between the diagram that describes order finding and the diagram that describes phase estimation. And pay particular attention to this initialization of register y. Let's define the inputs of the quantum order finding algorithm. First, consider the L-bit positive integer denoted by capital N. Capital L is the minimum number of bits it takes to represent this positive integer in binary. We have two different notations shown over here. On the left, we have a string of L bits. Each of these bits are specified by a subscript. And that subscript matches the power of 2 that bit gets multiplied by in this sum on the right. Let's examine this summation notation. We have a sum over an index j, beginning at 1 and finishing at L. Each of the terms in this sum have the same format. We have the bit n sub L minus j being multiplied by 2 to the power of L minus j. So that power over here, this exponent, matches the subscript. So that's why this is a convenient notation to use. So let's consider some examples. When j is equal to 1, then we're going to be dealing with L minus 1 in this subscript. And that corresponds to the leftmost bit. So this leftmost bit over here, it is going to get multiplied by 2 to the power of L minus 1. So that is the highest power of 2 present in this sum. Then if we go all the way to the other end, to the rightmost bit, that corresponds to j equals L. So when j is equal to L, we're going to have L minus L in the subscript. L minus L is 0, so that corresponds to n sub 0. And n sub 0 is going to get multiplied by 2 to the power of 0, which is 1. So the rightmost bit in this bit string of length L corresponds to the ones place. So at the furthest value over here on the right, we have the ones place, and then we have the twos place, and then the fours place, and we keep going up until we get to the highest power of 2. So that is binary notation. And we have a very convenient summation notation over here, and a very convenient subscript to specify each of the bits in this bit string of length L. So that is the first input that we're considering. Now let's consider another positive integer. This positive integer is denoted by lowercase a. A is between 1 and n minus 1. And it has a very special property. It is co-prime with n. In other words, the greatest common divisor of a and n is equal to 1. So we can write that as the GCD of a and n is equal to 1. GCD means greatest common divisor. A lot of the notation over here is very similar to the notation used when we're describing Shor's factoring algorithm. And that is not a coincidence. This order finding algorithm is actually the quantum subroutine of Shor's factoring algorithm. So that is why we have some shared notation present over here. So these are the inputs of the order finding algorithm. We have two positive integers, n and a, and they have a very special relationship. They are co-prime, and a has to be between 1 and n minus 1. Now, let's define some terms. The order of an integer, a mod n, is the minimum positive integer labeled by r, such that a to the power of r is equal to 1 mod n. We're dealing with modular arithmetic over here. So this is a term that we're defining. And this term over here, order, it shows up in the name of this algorithm. What are we trying to find with this algorithm? It is the order. And the order of what? We're looking for the order of the integer a mod n. Those are the two inputs. So we have a and n. They are the positive integers, which are the inputs. And we're trying to find the order of a mod n. And it's very important in this definition that we consider the word minimum. We're looking for the minimum positive integer, denoted by r, that satisfies this property. So there are other integers that could also satisfy that property. But we are specifically looking for the minimum. It is the smallest one. So we're going to be raising that integer a to the power of r. And we want to get 1 mod n. So in modular arithmetic, a to the r has to be equal to 1. And 1 is the multiplicative identity. So that is the definition of this term, which we are calling the order. Now let's define the period of a specific function over here. And this function is defined as a to the power of the input mod n. So again, we have a and n. These are the inputs to the algorithm. And we're using them to define a function called f. F is taking in an input, which we're calling g, and we're going to raise a to the power of g, and we're going to do that modulo n. So we're working with modular arithmetic. And what we want to do is define the period of this function. So the period of this function is the minimum positive integer r, such that if we evaluate this function at g plus r, we're going to get the same value as if we evaluate this function at g. And again, we're working with modular arithmetic. We're working mod n. So this value of r over here, this positive integer, is actually the same as the order. So why am I putting these two definitions next to each other? Why are we considering the order and the period of a function? Well, it's because order finding is a special case of period finding. So we are actually trying to find the period of a periodic function. And we're specifically considering this function, where we have a to the power of the input mod n. So let's have a look at why these two concepts are related to each other. So if we take this function and we consider the input g plus r, that's going to give us a to the power of g plus r. we can use exponential laws and split that up into two terms being multiplied together. We have a to the power of g times a to the power of r. But by definition, a to the power of r is equal to 1 from up here. That's because this r is the order of a mod n. So this a to the power of r is the same as the multiplicative identity. And we can just get rid of it because it's the identity. And then we're left with a to the power of g. And that is the definition of the function. And keep in mind, we're working with mod n. So this entire equation over here is mod n. We're dealing with modular arithmetic. So this is why this value of r is going to act as both the order and as the period of a periodic function. So just keep that in mind when we're dealing with this order finding algorithm. The order finding algorithm is a special case of a more general type of algorithm, which is called a period finding algorithm. And the goal of a period finding algorithm is to find the period of a periodic function. And here we have defined the specific periodic function that corresponds to the problem of order finding. Now that we have defined the inputs to the order finding algorithm, and we've defined these terms of the order and the period, we are ready to define the target of phase estimation. So that is that unitary operator that's going to show up in the phase estimation procedure. So the target of phase estimation is the L-qubit unitary operator that has the following action. We have two different representations of how this unitary operator acts on states. So this unitary operator acts on a register of L qubits. That's why we have a superscript L over here. So it's not acting on a single qubit, it's acting on an entire register of L qubits. And G is the label for that state of that entire register. So if we consider some computational basis state of L qubits, and we initialize it in G, and then we act with this unitary operator, it's going to produce the following state. It's going to produce the state that is labeled by G times A mod n. So we're doing multiplication mod n, and we're multiplying by the value A. You can see that to define this unitary operator, we need to know what the two inputs are. So those are the positive integers A and n. And this multiplication of the label is the action of this unitary operator. And we're always dealing over here with multiplication mod n. So we can multiply these two positive integers, and then we have to chop off the bit that contains any integer multiples of n. We're only interested in the remainder. So that is how modular arithmetic works. Now let's have a look at this other way of representing the action of this unitary operator. If this unitary operator acts on a state that is labeled by f of g, then it's going to turn this into the state labeled by f of g plus 1. So why does this work? Well, let's have a look at the definition of the function. We have f of g is equal to a to the g mod n. So if we have a to the g as the initial state, and then we multiply by another factor of a, that's going to give us a to the g plus 1. So we're going to have a to the g plus 1 as the label. And a to the g plus 1 is the same as the function evaluated with the input g plus 1. So we can just put g plus 1 as the input of the function, and that's the same as taking the positive integer a and then raising it to the power of g plus 1. And keep in mind that this is again mod n. So we're dealing with modular arithmetic. So these are two different ways of defining this unitary operator. So we have defined the action of this unitary operator that is the target of phase estimation. Now we are ready to see how we can adapt the phase estimation algorithm to the problem of order finding. This diagram depicts the quantum order finding algorithm. Time flows from top to bottom. Vertical black solid lines represent qubits. Each of the qubits are labeled at the top of the diagram. The qubits are organized into two registers. On the left, register X contains mu qubits. On the right, register Y contains L qubits. This value L is the same L that we encountered when we were defining the inputs of the order finding algorithm. So one of those inputs, capital N, is defined as an L-bit positive integer. That means L is the minimum number of bits that it takes to represent N in binary. So the size of register Y, which is the number of qubits in register Y, that is determined by one of the inputs. What about the size of register X? So what determines the value mu? Well, we have some freedom to choose mu. We need to take some things into consideration. First, we need to take into consideration the value of L. And we also need to take into consideration our tolerance for error. So when we perform a measurement at the very end of this algorithm, we might have some errors. And we need to make a judgment of what level of error is acceptable. So it's going to be a trade-off. Do we want to add more qubits to reduce the error? Or do we want to have less qubits and deal with a smaller register? So this is a trade-off we're going to consider. And there's going to be a nuanced explanation as to how we actually choose this value of mu. So L is fixed by the input N, but this mu is not fixed entirely. It depends on how much error we're willing to tolerate when we perform measurements. So let's examine this quantum circuit diagram. We can see a lot of quantum gates occurring in this diagram. We can see the Hadamard gate appearing at the top. We have H's inside of these boxes. They depict Hadamard gates, and they're being applied to single qubits. We can also see controlled unitary gates. This black solid circle is placed on all of the control qubits. And the target of these controlled unitary gates, the target is actually an entire register of L qubits. So we have a sequence of controlled unitary gates. And over here we can see the inverse quantum Fourier transform being applied to register X, and that involves mu qubits. So this is the mu qubit inverse quantum Fourier transform. And at the very end, we can see measurement gates. And poking out of these measurement gates, we can see double lines. Those double lines are not solid lines. That is because we're trying to distinguish these lines as classical bits. So these double lines are representations for classical bits. So that's what we get when we measure qubits. When we measure qubits in the computational basis, we're going to measure one of those two computational basis states. So we're either going to get a 0 or a 1. And have a look at the labels for these bits at the bottom. We can see that there are two numbers in the subscript. The first number is gamma, and the second number over here is -1, then -2, and it goes all the way to minus mu. So previously, when we were looking at the exact case of the quantum phase estimation algorithm, we didn't need this gamma over here. But now we're going to need another index gamma to describe these bits. So next, later in this video, we're actually going to explain what this gamma is. And this comes as a consequence of the initialization of register Y. So let's have a look at what the initialization of register Y is. In the previous video, we had the eigenstate lambda over here. But now we're not initializing in an eigenstate of the unitary operator. Instead, we're initializing in a superposition of eigenstates. And that superposition of eigenstates is equivalent to the L qubit state labeled by 1. Or alternatively, we could also describe it as a string of length L. So we have a bit string of length L, and the first L minus 1 of those bits are all 0, and then the final bit is 1. So we have 0, 0, 0, 0, all the way up to the second last bit, and then the final bit is equal to 1. So that is a representation of 1 in binary. It's an L-bit representation of that state. And this state over here is actually equivalent to a superposition of eigenstates of this unitary operator. So that is very important. This is a very nuanced point that allows us to perform this order finding algorithm. Let's have a look at 4 key stages in this algorithm. This green snapshot over here allows us to see what happens just after initialization. So this is the initial state of both registers. Register X is initialized in all zeros. So these are all the single qubit computational basis states labeled by 0. So that's a string of mu zeros over here. And what about register Y? Well, almost all of these are 0, except for the last one, which is 1. So that is our initial state. And if we look at the green snapshot, we will be able to mathematically describe the initial state. After we apply these Hadamard gates to all of the qubits in register X, we're going to create a superposition of all of the computational basis states in register X. And that is going to be described in this blue snapshot. So the green snapshot is initialization, and the blue snapshot is creating superposition in register X. It's a superposition of all the computational basis states in register X. And we do that by applying these single qubit gates. So these Hadamard gates, they are single qubit gates being applied to each of the qubits in this register. In total, there are mu of these gates being applied to all mu qubits in register X. Then the next part of this algorithm involves this sequence of controlled unitary gates. And as we said, this is the notation for these controlled unitary gates. Observe that this first controlled unitary gate has the control symbol over the qubit denoted by x sub 0. And then the next one has the control qubit as x sub 1. And then if we skip over all the intermediate steps, then we get to the second last one, which is associated with the control qubit x sub mu minus 2. And then finally we have x sub mu minus 1 acting as the control qubit for this final controlled unitary gate in this sequence of gates. And the target of these controlled unitary gates are always the entire register. So we have this entire register of L qubits that are acting as the target. And over here in the middle, you can see some vertical lines, vertical dots in between these vertical lines, and they represent the fact that we have omitted all of those intermediate gates in this sequence of unitary gates. So you can see horizontal dots, they represent we have omitted qubits in this register. Those are the intermediate qubits in the middle. And then we have those vertical dots, which tell us that we have omitted gates over here as well. And the vertical lines, they represent qubits. So those are all individual qubits. And the qubits are being fed in over here as inputs, and then they're coming out as outputs. And this action over here is going to change the state of those qubits. And at the very end of this sequence of controlled unitary gates, we're going to get to the red snapshot. So this red snapshot shows us what happens after we've applied all of these controlled unitary gates. So that U is the target of phase estimation. And it is the eigenstates of U that are appearing in this initialization. So we're not initializing in a single eigenstate. Instead, we're initializing in a superposition of many eigenstates. And each of those eigenstates are indexed by the value gamma. And that is the same gamma that shows up in these labels for the bits at the bottom when we perform a measurement. Let's have a look at this inverse quantum Fourier transform. When we apply this mu qubit inverse quantum Fourier transform to register X, we're going to have a different state. And that state is the state just before measurement. And we're going to mathematically describe that with the purple snapshot. So this purple snapshot shows us the quantum state just before measurement. And we're going to see that this purple state is going to be perfect. It's just going to allow us to get the answer that we're looking for. But we always have to consider that there are errors. So even though it is the perfect format, we might get some errors. And that error is going to be mitigated by the choice of mu. So we want to reduce the error, but we always have to consider the trade-off. We can reduce the error by making mu really, really large, but it might not be practical to have a register of qubits that is extremely large. We have to take practical considerations into account. And it might also be unnecessary to include a really, really large value of mu. So that is the nuanced argument we're going to consider when we choose the value of mu. Now that we've seen this diagram, we're ready to have a look at each of the snapshots. And pay close attention to the exponents in these controlled unitary gates. So have a look at and see that these exponents, they have powers of 2. So we have 2 to the 0, 2 to the 1, all the way up to 2 to the mu minus 1. And those exponents over there, they actually match the subscripts for the qubits. So see the labels at the top of register X? These subscripts are exactly the same as these powers over here. And they're associated with which of those qubits are acting as the control in this controlled unitary gate. So we're going to need that when we look at the red snapshot. Now let's move over to the green and the blue snapshot. The green snapshot shows the quantum state of both registers immediately after initialization. The notation on the left is very similar to what we saw at the top of the quantum circuit diagram earlier in this video. So we can see the first, second last, and last qubits in register X on the left and register Y on the right. All mu qubits in register X are initialized in the state labeled by 0, and the first L-1 qubits in register Y are initialized in the state labeled by 0. But the final qubit in register Y is initialized in the state labeled by 1. So this depiction is valid if mu and L are both larger than 4. What if mu or L is equal to 4? Well, then we have to get rid of these dotted lines because we're no longer omitting qubits in the middle. What if mu or L is less than 4? So what if mu or L are equal to 1, 2, or 3? Well, then we have to remove some of the qubits shown over here. So we get rid of some of those qubit states, and then we're going to have a valid description of what's going on. But for practical examples of the order finding algorithm, we're not actually going to be dealing with those small values. Mu and L are going to be much larger than 4 for practical applications. So practical applications are going to involve using the order finding algorithm as a subroutine of Shor's factoring algorithm. So let's have a look at how we can interpret these initial states. In the condensed notation, the state of register X is labeled by a single 0, and then we put a mu in the superscript. Similarly, the state of register Y is labeled by a single 1, and then we put an L in the superscript. Alternatively, we could put a string of bits inside of these kets as labels. So for this state of register X, we could put mu zeros in there as a string. And those mu zeros are going to represent the value 0. And this is going to be a binary representation using mu bits. Similarly, we can represent the value 1 using L bits. And that would entail having L-1 zeros followed by a 1. So that's exactly the same format that we have on the left over here. L-1 zeros followed by a 1. That encodes the value of 1 using L bits. And we can think of those bits as labels for qubits. Everywhere where you have kets next to each other in this notation, you can implicitly imagine a tensor product symbol in between the kets, because we're taking the tensor product of these single qubit states and we're turning them into multi-qubit states. So on the right in this condensed notation, we're not dealing with a single qubit computational basis state. We're dealing with the collective state of an entire register of qubits. So this 0 is actually 0 for the entire register X, and this 1 is 1 for the entire register Y. So now we've thoroughly explored this notation that appears in the green snapshot. Let's move on to the blue snapshot. The blue snapshot tells us the quantum state immediately after we apply a Hadamard gate to all of the qubits in register X. So that's shown in this notation on the left. We have a H being applied to this ket with a 0. So this ket with a 0, that shows the initial qubit state, and then we're applying this single qubit operator, the Hadamard gate, to that qubit state. And we're doing this to all of the qubits in register X. So we have mu operations over here. And we can write that in a far more condensed format. We can write this as H with a tensor product mu in the superscript. So we're putting a tensor product there so we don't confuse this as being an exponent. If we were to write H with an exponent in the top, that would mean we're applying H multiple times to the same qubit. But that's not what we're trying to communicate here. So what we're trying to communicate is that we're applying a Hadamard gate once to each of the qubits. So there's a separate Hadamard gate for all of the qubits, and it's only being applied once. So that's why we have this tensor product sign. And we're using the condensed notation for this state over here of this is the initial state of register X. And another way we can represent this is as a superposition of the state 0 and the state 1 being tensor producted with itself mu times. So where does this come from? Well, when the Hadamard gate is applied to this state labeled by 0, it's going to turn into a superposition of 0 and 1 with a normalization coefficient of 2 to the minus 1/2. And because we have mu copies of that, we can use exponential laws and combine that into a single normalization coefficient. So this is the same as going from the Pauli Z eigenbasis to the Pauli X eigenbasis. So that's just an alternative notation for this same procedure of applying all of those Hadamard gates to each of the qubits in register X. The end result of that is to produce this superposition of all of the computational basis states. So if we took all of those superpositions of 0 and 1, and then we tensor producted that mu times, we would get all of those different terms. And all of those terms would actually be different representations of all of the computational basis states. So one way of labeling all of the computational basis states is with this index G, which goes from 0 up to 2 to the mu minus 1. So we can label that using decimal notation. But we can also label this in binary. We can use bit strings to label all of those computational basis states. And that type of labeling system is very convenient when you've got this form over here, where you start with a superposition of 0 and 1. Because then, when you perform all of those tensor products, you're going to get strings of zeros and ones. And when you complete this entire procedure, you're going to end up with strings of length mu as the labels for all of those computational basis states. So that's just different ways of expressing that superposition of all of the computational basis states in register X. What is going on over here in register Y? So we've gone from 1, and now we're calling this f of 0. So what is going on there? Well, to see what is happening in this relationship, we have to look at the blue box. So over here, we're defining a new type of state. So we're labeling this state as f hat as a function of gamma. And this state is going to be defined as a superposition of all of the states labeled by f of g with these complex coefficient factors over here. So these complex coefficient factors, these are actually complex exponentials of the form e to the minus 2 pi I g gamma divided by r. So r to the minus 1, that is the same as dividing by r. And we have a sum over this index g, and this sum goes from 0 to r minus 1. And the normalization coefficient is r to the minus 1/2. So r is appearing in multiple places in this definition. What is r? Earlier, we defined r to be the order of A mod n. R is also the period of this periodic function f. So R is both the period and the order of different definitions. So if we take those inputs, A and n, those are the inputs to the order finding algorithm, we can define R as the minimum positive integer such that A to the R is equal to 1 mod n. That is by definition the order of A mod n. And we also saw the alternative definition where we define this function f of g and we look at the period of this function. So this is a periodic function and the period of this function is r, and that's exactly the same as the order of A mod n. Now let's re-express this equation in terms of these f of g states. If we do that, then we're going to have to switch the label of this sum. So we're going to have to switch the index that we're using. So instead of g, we're going to use gamma. And we're also going to have to take the complex conjugate of those complex exponentials. So now we're going to have e to the plus 2 pi I g gamma times r to the minus 1. So note that g and gamma have a very special relationship. They are a special pair of variables. So when gamma is fixed, g is going to be summed over. And when g is fixed, gamma is going to be summed over. And they're both appearing together in these complex exponentials. So this is a very important expression that we're going to be using later in this video. And let's consider a special case of this bottom left expression. Let's set g equal to 0. If we set g equal to 0, then this function is going to evaluate to a to the power of 0. And a to the power of 0 is equal to 1. So that explains this here on the left. And another way we can express this is using the definition that we have over here on the left. So if we set g equal to 0, then all of these complex exponentials are going to have a 0 in the exponent. So we're going to have e to the 0, which is 1. So all of those are just going to turn to 1. All of those coefficients will be 1. And then we can reveal this relationship over here. So the state labeled by 1, that is equivalent to a superposition of all of these f hat states. And these f hat states, they're very special. They are actually eigenstates of the unitary operator, which is the target of phase estimation. So when we initialize this register y at the beginning, we're initializing it in a superposition of eigenstates. So we're not initializing it in a single eigenstate like we saw in the previous video, where we had the exact case of the quantum the quantum phase estimation algorithm. Now what we're doing is we're initializing in a superposition of eigenstates. So that is allowed. So because we don't know how to prepare these eigenstates at the beginning, we can prepare a superposition of them. That's something that we can initialize at the start. So why can we not prepare these eigenstates at the beginning of the algorithm? Well, it's because in the definition we have r. So r is part of the definition, but r is the unknown. That's what we're trying to find using this order finding algorithm. So that is why we're not allowed to initialize in these eigenstates. So we have to use this trick, and we have to initialize in a superposition of eigenstates. And that's why we have to introduce this index gamma. So gamma is going to specify which of the eigenstates we are dealing with in this superposition. So that is what's going on in this blue box, and it shows you what is happening over here in this state. So this is the state that is being shown in the blue snapshot. So that's after that creating superposition stage in the algorithm. What about this green box? Well, this green box defines a coefficient alpha sub gamma k. And this coefficient will show up in the next part of this video. And the reason I put this over here is because it is essential in the working that we need to do to determine what mu needs to be. So we're going to have to determine mu. We want to find a general way of determining a choice of mu, given that we have a value of L. So that is what we're going to have to do later. And that's what this green box is going to help us with. So pay close attention to what's going on in this green box, because this coefficient is going to show up later. And now that we've seen this green snapshot and this blue snapshot, let's move on to the next two snapshots. Those are the red and the purple snapshots. In this red box at the top, we can see the eigenstates of the target unitary operator. These eigenstates are the same states that we encountered in the blue box. So they are labeled by f hat as a function of gamma. And we can express these states as a superposition of states that are labeled by f as a function of g. So that is the definition of these states that we saw in the blue box. So what we're going to have is a normalization coefficient of r to the minus 1/2, and then a sum over g going from 0 to r minus 1. And then we will have the complex exponential factors that have the form e to the minus 2 pi I g gamma divided by r. And then we can bring in this unitary operator inside of this superposition, and we can act with this unitary operator on these states that are labeled by f as a function of g. In the beginning, when we actually defined this unitary operator, which is the target of phase estimation, we saw that when it acts on one of these states, which are labeled by f as a function of g, it actually maps them to f as a function of g plus 1. Now, why is that the case? Well, f of g, that's the same as a to the power of g, mod n. We're dealing with modular arithmetic. So if you have a to the power of g, and then you multiply by another factor of a, mod n, that can be combined together to give you a to the power of g plus 1. So g plus 1 occurs in the exponent. And then that, by definition, is the same as the function evaluated with this input, g plus 1. So just keep in mind that these functions are defined using modular arithmetic. We're working mod n. N and a are the two inputs to this order finding algorithm. So that gets us to this stage over here. So we have brought this unitary operator inside of the superposition, then we've acted on each of the states in this superposition, and that's gotten us to this alternative superposition. Now let's change this index from g to k. So let's see how we're going to do this. G starts at 0, and then it goes up to r minus 1. K starts at 1, and it goes up to r. So g plus 1 is equivalent to k. So when we have f as a function of g plus 1, that's equivalent to f as a function of k. And when g appears in this complex exponential, we can substitute it with k minus 1. So that's how these two indices are related to each other. K minus 1 is the same as g, and g plus 1 is the same as k. So now we can see that these are two equivalent expressions. We're just using a different index in the summation. And here's another thing that we can do. We can identify that we can break this complex exponential up into two factors. And we can take that minus 1, and that's going to cancel the minus sign out the front. And then we can pull out a complex exponential factor which does not depend on k. So that is equal to e to the 2 pi I gamma times r to the minus 1. So this is the same as the ratio of gamma and r inside this complex exponential. So we have pulled that factor out, and what remains inside is e to the minus 2 pi I k gamma times r to the minus 1. So this is the remaining other part of this complex exponential. So all we've done is used exponential laws, and we've split this complex exponential factor into two factors. And then the part that does not depend on k, we have pulled outside of this summation. Now in this format, we can identify that this is actually the definition of this eigenstate that we started with. But we have to be a little careful, because the initial and final entries in this sum are not the same as the ones that we have up here with g. So let's see why these are actually equivalent definitions. So if we consider the case where k is equal to r, so what is that going to be equal to? So if we have k equal to r, what complex exponential are we going to have? So if we put r as a value of k over here, that is going to cancel with this r to the minus 1. So k is going to be equal to r, and it's going to multiply with r to the minus 1, and that's going to give 1. So the only thing we'll be left with is gamma in this complex exponential. So we have e to the minus 2 pi I gamma. And gamma is an integer. And what we have is an integer multiple of 2 pi. So that's just going to give us 1. We're going to have 1 as the value of this complex exponential. And what about over here? We're going to have f evaluated at r. And because this is a periodic function and r is the period, this is the same as f evaluated at 0. So when k is equal to r, we have exactly the same scenario as if k was equal to 0. So if we go up to this expression up here where we see g equals 0, g starts at 0, when we set this equal to 0, we're going to have e to the 0, which is equal to 1. So that's the same coefficient that we found earlier. And if we set g equal to 0 over here, we're going to have f as a function of 0. And as we stated before, because of the periodic nature of this function, f evaluated at 0 is the same as f evaluated at r. So that means that this term at the end of this sum, corresponding to k equals r, this is exactly the same as if k was equal to 0. So all we have to do is just nudge that term back to the start. And because this is a sum, and adding these states in a superposition, that's commutative, we're allowed to swap the order of these states in a superposition. So that means that we have exactly the same state that is present in the definition that we saw in the blue box. And all we have to do is just change the bounds over here. So we can change that index as going from 0 up to r minus 1. So all of the terms, including 1 up to r minus 1, they are the same. The only difference is that we have this k equals r term at the end, but in the original definition, that term corresponded to this k equals 0 term at the start. So we have a demonstration that this is equivalent to that eigenstate. And this is the eigenstate multiplied by an eigenvalue. So in this red box, we have an eigenvalue equation. The target unitary operator is acting on one of its eigenstates, and that is giving us this eigenvalue multiplying the eigenstate. And this ratio of gamma and r, which is written as gamma times r inverse, that's the multiplicative inverse or the reciprocal, this is playing the role of phi. So before, when we were considering the exact case of the phase estimation algorithm, we had phi in this complex exponential acting as an eigenvalue. So this is actually the phase. Gamma divided by r, that is the phase that defines this eigenvalue, which is associated with this eigenstate. And this phase is specified by gamma. And gamma also specifies which eigenstate we are dealing with. So this is really important information in this red box. It shows us why these states that are labeled by f hat as a function of gamma, it shows us why they are eigenstates of the target unitary operator. And because they're eigenstates, if we have a superposition of them, we can use that as a trick to initialize register y. And that is it for this red box. Now let's move over to this red snapshot. And the red snapshot shows us the quantum state after we've applied the sequence of controlled unitary gates. So this is very similar to what we had in the phase estimation video. And this is the same format over here. The only difference is the state of register y. So instead of having a single eigenstate, we have this state f of 0. And this is actually equivalent to 1 being the label over here. And it is a superposition of all of these eigenstates, which are specified by gamma. So what we can see is that if we have this sequence of unitary gates, we can rewrite that in this condensed form. So what is going on in this top expression? Well, we are expressing all of those computational basis states as bit strings. So we are considering the individual bits. And these individual bits are acting as labels of qubits. And so we have mu of them over here. We're taking the tensor product, and that's giving us all of those computational basis states. But if we express it in this format, we need all of these mu sums over here. And these sums have to go over all of these bits, which can take on values of 0 or 1. This format is very convenient when we're expressing these controlled unitary gates in a sequence, because we can see all of these terms in the sequence. We can see the first gate that's applied, then the second gate, and then we have dots to show all of those omitted gates, and then we have the second last one and the last one. And we can use exponential laws to combine all of these unitary gates into a single unitary gate being raised to the power of g. So if you use exponential laws, you're going to get a sum of all of these exponents. So we can turn that multiplication into addition within the exponent. And that's going to give us this G. And this G that's in this exponent is exactly the same as the label for these computational basis states. So that's what makes these controlled unitary gates. They're controlled because the states of these control qubits are impacting whether or not we apply those unitary gates. So if any of these bits are equal to 0, that means these gates get deactivated and they're not applied. But if they're equal to 1, it means we do apply them. So that is why this big lengthy expression is equivalent to this more succinct expression over here. What happens if we apply u to the power of g to the state labeled by f of 0? If we apply a single u to this state, that's just going to increase it by 1. So this 0 is going to go up to a 1. And then if we apply it again, then it's going to go up to 2, and then to 3. And we can keep going all the way up to g. So it's just like we saw in that blue box. Every time you apply this unitary operator to a state labeled by f of some entry over here, we're going to add 1 to that entry. Because this unitary operator actually multiplies by a mod n. That's the action of this unitary operator. It takes the label of this state and it multiplies it by a mod n. And because this function is giving us actually an exponential, it's raising a to the power of the input, then if we multiply by another factor of a, we're just going to add 1 to the exponent. So that's an extra power of a. So that gets us from this state over here to this state, which is labeled by f as a function of g. So now the input to this function, which is the label over here, is the same as the label for this state. We have g as the label for this state of register x, and we also have g as the input to the function, and this function, f of g, it is the label for the state of register y. So that is what is going on after we apply that sequence of controlled unitary gates. That is it for the red snapshot. Now let's move on to the purple snapshot. This is what happens after we apply the mu qubit inverse quantum Fourier transform to the register on the left, which is register x. And you can see what has happened from this state over here at the end of the red snapshot and this first expression in the purple snapshot. So we can see that we have the notation f sub 2 to the mu, and then we have a dagger. 2 to the mu, that's the dimension of the Hilbert space of a mu qubit system. F is for Fourier, and this dagger is denoting the Hermitian adjoint. That's because we're dealing with the inverse quantum Fourier transform. And it's specifically for mu qubits, because we're applying it to a register that consists of mu qubits. So this is a concise way of expressing that state, and now we can unpack the details. So the inverse quantum Fourier transform, that can be expressed as this superposition, where we have another normalization coefficient of 2 to the minus mu on 2. Then we have a sum over an index k, that goes from 0 up to 2 to the mu minus 1. And then we have these complex exponential factors of e to the minus 2 pi I kg times 2 to the minus mu. And note that we have a negative sign in the complex exponential. That's because we're dealing with an inverse quantum Fourier transform. And then we have the label of these states in the superposition are equal to k. So k shows up in this complex exponential. So we've taken that input state g, and we've created this superposition. And now the label is k. So that is what's going on when we apply the inverse quantum Fourier transform. Then let's have a look at this f of g state. Now in that blue box, we saw a way of expressing these f of g states in terms of the f hat of gamma states. So this is a superposition of these f hat states. So this is equivalent to that single f of g state. So now we have this mess of superpositions. So let's rearrange these summations. We can bring out the normalization coefficient of r to the minus 1/2. So we can move that all the way to the left. And we can pull out this sum over gamma, and we can move that over to the left. And then we can take these two sums of over k and g, and we can also put them on the left. And we can smush together all of the coefficients. So these 2 to the minus mu on 2's, they can multiply together, and they can give us 2 to the minus mu. So we're just squaring that. We're getting rid of the half, and that's just giving us 2 to the minus mu. And what about this exponential factor? Well, we have e to the 2 pi I showing up in both of these factors, and we can also see g showing up. So over here, we can see gamma times r to the minus 1/2. That's showing up over here. And then we're subtracting off k times 2 to the minus mu. So that's inside these brackets over here. And both of these terms have g in common. So we can factor that g out. And we can also use exponential laws, and then we can raise this entire complex exponential to the power of g. So this is just rearranging this big mess of superpositions. And now we have three sums over all of these coefficients and then these states over here. So this mu qubit state, that is describing register x, and then register y is described by this L qubit state. So K is the label for those register X states, and the register Y states are labeled by these F hats. Now that we have this relationship over here, let's do a slight modification of the label K. We're going to add capital phi sub gamma to all of the values of K. So inside this exponential, we're going to add capital phi sub gamma. And also inside the label of this register X state, we're going to add phi sub gamma. But what we're going to do is we're going to have addition mod 2 to the mu. So we're going to use modular arithmetic. So this is not mod n, this is mod 2 to the mu. And mu is the number of qubits in register X. So why is this equivalent? Well, we're dealing with a cyclic type of relationship here. So when you graph out these values of these complex exponentials, they're going to lie somewhere on the unit circle in the complex plane. And if you shift all of them, that's the same as rotating all of them in the complex plane. So what we can do is we can redefine this index k, and we can just give it a shift. And then we can see that this expression over here is equivalent to this expression up here. So when we implement modular arithmetic, we're still going to have all of the states in the superposition. So all of the same states are going to be accounted for when we range from k equals 0 up to 2 to the mu minus 1. We're just going to shift them over by this additive factor of capital phi sub gamma. So that's what we're doing over here. We're just applying this shift to the value of k. And because of modular arithmetic, that shift is just going to push up all of those values, and then they're going to turn into smaller values as well. Now, what is going to happen in this complex exponential? Well, just because of that cyclic property of the complex exponential, that shift is just going to rotate all of those complex amplitudes. So it's still going to be equivalent. We have an equivalent expression over here. Now, the reason I'm adding this shift is because now we can incorporate that coefficient that we defined in the green box. So that coefficient alpha sub gamma k. So this coefficient is determined by two values. We need gamma and we need k to determine this coefficient. So we have these two labels for that coefficient alpha. And then we have this more condensed format over here. So we have a sum over gamma and a sum over k. Now we're going to get to an approximation. So we want to choose a value of mu that ensures that this approximation holds. So we want the amplitude in this superposition to be really large for k equals 0. And we want the amplitude for all other values of k to be really, really small. So we want the chance of measuring any of those other values of k to be very negligible compared to the chance of measuring k equals 0. So that's what we're aiming to do here. We're aiming to maximize the probability of measuring the states that correspond to k equals 0. And if that is satisfied, if this amplitude is almost 0 for all other values except k equals 0, where it's equal to approximately 1, then we're going to have this approximation hold. So note that this k disappears now because we're only interested in the k equals 0 state. But we still have a superposition. We have a superposition of these r values. So we range from gamma equals 0 up to r minus 1. So there is still a superposition. So we are not going to be guaranteed to measure a single value, as was the case in the previous video where we had the exact case of the phase estimation algorithm. Now we have several options that we can measure, and those options are specified by the index gamma. Let's have a look at the purple box. It's going to give us more insight into this notation. So this capital phi sub gamma can be expressed as this quantum state with mu terms over here. And each of these are single qubit states. So each of these little phi sub gamma, comma, -1, little phi sub gamma, comma, -2, all of these guys are bits. They are labels for these computational basis states of a single qubit system. And you can imagine implicitly there are tensor product symbols in between these kets. And the reason we now have an extra gamma over here is because we're not guaranteed to have one option that we're measuring. We're measuring our different options. Those are the options that we have when we perform the measurement. So we have a superposition at the purple snapshot, and we're only going to be measuring one of those values. But those values are specified by gamma. So that's why we need this index. And you can see that there are several different ways we can express this. This capital phi sub gamma is actually a bit string of these mu little phi terms. So it's very similar to the notation that we had in the phase estimation algorithm video. And this bit string can also be written as this tensor product of mu individual qubit states. So that's just notation to help us clear up what's going on in this final expression over here. And another very interesting thing is that gamma times r to the -1, that is approximated by this capital phi sub gamma times 2 to the minus mu. So this capital phi sub gamma, that is a positive integer. It is a bit string. So it is a binary representation of a positive integer. And we have to multiply that by 2 to the minus mu to get this binary fraction, which we can write as 0 point this bit string, or we can write it in summation notation. And each of these subscripts correspond to the power of 2 that this bit is getting multiplied by in this sum. And you can see j goes from 1 all the way up to mu, and that accounts for all of these bits over here. So we're only going to be measuring mu bits. And the level of precision is going to be determined by our choice of mu. And we're going to see that in later videos. We're going to see how to choose this value of mu, which guarantees that this approximation holds and that we actually get a decent approximation for gamma times r to the -1. Now you might be wondering, where is the order? We haven't found the order. We are actually just measuring gamma times 1 over the order. So we're measuring a factor times the reciprocal of the order. We don't have the order yet. We have to do some post-processing. So once we perform the measurement at the end of this order finding algorithm, we have to process that measurement, and we have to see if we can extract the value of r from that measurement. So this quantity of gamma times r to the -1, that is what we're actually going to try and approximate. And we're not going to be directly measuring that. Instead, we're measuring an approximation for that. We're measuring this bit string, which is capital phi sub gamma. So we're going to be doing a lot more analysis, and we're going to be seeing how this algorithm works. And we're going to be analyzing the performance of the quantum order finding algorithm. So it's just very important to familiarize yourself with all of this notation. So this notation provides a very detailed mathematical description of these snapshots. So we have the red snapshot before the quantum Fourier transform, and then the purple snapshot after the quantum Fourier transform. And specifically, we're applying the mu qubit inverse quantum Fourier transform. So by convention, I'm calling the operation that has a minus sign in this complex exponential, I'm calling that the inverse quantum Fourier transform. Other conventions do exist, and sometimes people will actually call this the quantum Fourier transform. So it is confusing, but as long as we stick to the same convention, we need to be consistent and mindful of that. So that's why we have this dagger symbol over here. So in the next video, we're going to be analyzing the performance of this algorithm, and we're going to see how we can extract the value of r from the measurement at the end of the this quantum algorithm.